Okay, are there any questions from last class? Anybody? Okay, so what we did last class was to define quantities such as impedance and admittance, and then we looked at the physical meaning of admittance, and particularly we looked at the real part of admittance. Imaginary part we are not dealt with. So what does the real part of admittance mean? Anybody? What is its significance? What does it show?
The power which is the system takes.
Yeah, right. So right, and so if the power is coming in, you will get one sign. If the power is going the other way, you will get the other sign, and we will work this out as we go on. So now I wanted to raise a question. We said that we have differential equations, and we said that we can solve them as eigenvalue problem depending on the boundary conditions. We can have boundary conditions, need boundary conditions like open open or closed open, open closed, and so on. But then we said that the point was raised as to why a rocket nozzle would have exactly a closed condition and why it shouldn't be different and so on, and I agreed that a nozzle will leak out some acoustic power, so you can have some non-zero value of admittance and so on. So having said that, and having thought of the problem as an eigenvalue problem, it is quite likely that you would get a complex eigenvalue, and you will get a real eigenvalue only if you have either velocity 0 or pressure is 0 at the end, as we saw in the simple problems that you worked out. So let me, before I proceed, try to figure out what is meant by a complex frequency. Anybody know what is a complex frequency? Yeah, what is the meaning of complex frequency? I mean, I can think of frequency as cycles per second, so what does it mean?
The imaginary part will cause a decay or an increase in the amplitude.
And what will the real part indicate?
The real part will indicate the frequency.
Yeah, so that's absolutely right. Let's look at this carefully before proceeding further. So let's think of omega as omega real plus I times omega imaginary, and let's look at e power I omega t, which is e power I times omega real plus I times omega imaginary times t, which if you multiply out we will get e power omega I omega real t times e power I times I is minus 1, so e power minus omega imaginary t. So this is the periodic part, and this is the exponential growth or decay. If omega imaginary is positive, you have exponential decay. If omega imaginary is negative, you will have exponential growth. So I'll say this is exponential growth or decay. So if you have only a real frequency, that means you have periodic component and it's neither growing nor decaying. But if you actually end up with eigenvalue which has complex part, the imaginary part would indicate what is called a growth rate or a decay rate. So imaginary part frequency will give growth or decay. So I hope this part is clear. I'll just pause for a minute for you to make notes. Okay, so let's think of a situation when frequency is real. Now we were speaking about the impedance tube, and we said that was nothing but a tube with a loudspeaker at one end and some termination on one side, and you have a lot of pressure transducers mounted, or you have one microphone which you are moving along. Now imagine we turn the speaker on, loudspeaker on. Actually in the beginning the amplitude will grow, and the growth will happen over half a second, 1 second or quarter second of that time scale, and then it will stay steady. And why will it stay steady? Because initially you are putting in power and there are some losses, but as you increase the power you lose more, and eventually you reach a kind of situation where whatever you put in is equal to whatever is lost, and then you maintain steady amplitude. So that would mean there is no further growth or decay. So actually this reaching this final amplitude is a nonlinear phenomena, but we will not worry about that, and we will keep the frequency now as real, because we are not having a growth or decay, and then we still try to apply linear theory. So just to quote this over quoted statement, all theories are wrong but some theories are useful. So I think this is we have to see if it's useful, then it works. So I must agree that I am doing this sleight of hand, because anytime you reach in principle you are reaching a limit cycle, because the oscillations are growing and then saturating off. So limit cycle is indeed a non-linear phenomena. There is nothing called a linear limit cycle, but then we will set up the experiment at low amplitudes, and then we will say that the propagation and of the waves is linear, and that is a sleight of hand, and hopefully we will get good results. That is the idea. So like I said, all theories are wrong but some theories are useful. So we will only after you do the theory you will know whether it is useful or not. So we will initially stick with real omega, and then you will try to see, once you know the admittance of whatever is the termination, whether we can translate it into had there been no loudspeaker, whether you get a growth rate or decay rate. So that is the ultimate objective, that is to look at the stability of the system. For example, suppose you found the stability of your impedance of a propellant or something by putting a loudspeaker, exciting it, checking what the amplitude of the wave is coming and so on, and then that is not an end by itself for us. In the end what we want to do is we want to solve for the eigenvalue problem without any loudspeaker and see if the system will get self-excited. That would mean a self-excited system would mean this would be a growing term e power alpha t, and if it is a stable system it will be a exponentially decaying term. So that is what we are interested in eventually finding out. So we will do it as two steps. First we will deal with how to determine the admittance of a termination by using this impedance tube technique. That is essentially a forced experiment. That means you force the sound with a loudspeaker, and then we will see if we can translate it into some kind of self-excited problem where you leave a system alone and see what happens. I hope this approach is clear. Sounds a little crooked, but that is what it is, but once you work out you will see it is not all that crooked. So in this process we are doing the experiment with the loudspeaker with a real frequency. That means we are setting up the experiment in some kind of steady state. Okay, is that clear? So let me draw the picture once again. So we have, so this tube is the impedance tube, and you have a sound source, and you have a microphone. This is just symbolic of doing a traverse in the entire setup, and as I mentioned you should have a reference microphone here, and you can either traverse with one microphone or you can put 20 microphones and get the acoustic field, and you always need a reference to determine the phase. Phase is by comparing signals from two different locations, so two different transducers. So we need always a reference microphone either at the end or someplace, and then we have this. This is the termination or the material you want to study, and then let us say we have a rigid backing. To hold this in place and to make sure that nothing comes in from any other side and so on. So we will start with our equations. Usual equation P hat equal to A e power I k x plus B e power minus I k x. So I will work out this problem in the harmonic domain or the frequency domain. That means it is implied that p prime equal to p hat e power I omega t, and then you have to take the real part and so on and so forth. But we will just deal with the complex amplitude, and then in the end if you want to find the instantaneous pressure, we have to multiply it by e power I omega t and take the real part. Is that clear? Okay. So let us now try to do some algebraic manipulations to get an expression for the amplitude, which is the amplitude of this complex number, which is p hat times p hat star, its complex conjugate, and take the square root, and that would be the amplitude at each location in a standing wave. So you have a complex amplitude, that would mean it will have both the amplitude information as well as the phase information. Phase means how the wave is going up and down with respect to how the pressure is going up and down at another location. So we want to try to get a expression for the amplitude separately and phase separately, and then we will try to see what is the nature of the function. So we can say that in general A, B are complex. So you can say A equal to A e power I phi 1, B equal to B e power I phi 2. So if you put that in here, so you will get A e power I times kx plus phi plus B e power minus I times kx minus phi. Now we will go to trigonometry to do some algebra. So this can be written as A cos kx plus phi plus I sin kx plus phi plus B into cos kx minus phi minus I sin kx minus phi. So now what we can do is we can collect the real part together. Yes, and make sure there is some problem. Oh yeah, thank you. Yeah, thanks a lot. Anything else? Okay. So now what we want to do is to we wish to club the real parts together, imaginary parts together, and then we can easily find the amplitude. So we can say this is A so this should be phi 2 actually, sorry. Is this okay? If there is any mistake, please point out. So if you want to take the find the amplitude of this, so we can say p hat squared equal to, we just take square of that plus square of this. So you will get A squared cos squared kx plus phi 1 plus B squared cos squared kx minus phi 2 plus 2ab cos kx plus phi 1 multiplied by cos kx minus phi 2 plus the other set of terms A squared sin squared kx plus phi 1 plus B squared sin squared kx minus phi 2 minus 2ab sin kx plus phi 1 sin kx minus phi 2. So now if we try to add these terms, it simplifies a lot. Yeah. So this term, we know that sine squared theta plus cos squared theta is 1. So this whole term simplifies to a squared, and similarly here again we get sine squared plus cos squared. So you will get that is 1 plus 2ab into cos kx plus phi 1 cos kx minus phi 2 minus sin kx plus phi 1 times sin kx minus phi 2. So this can be simplified. You are having the form cos a cos b minus sin a sin b, which is or the form cos a plus b. So we can replace this term. I hope I have the right result. So this is the expression for the amplitude of the standing wave. So just note that when we wrote p hat here, there is the complex amplitude. That means that at each location it's a complex number. That means its amplitude, that is this is actually square of the amplitude, gives actually the amplitude of the standing wave. But the phase actually represents how the wave is moving with respect to other parts of the wave. So I hope this difference is clear. So now if you put microphones at different locations, at each location if you measure the amplitude, this is the kind of variation that you would get. In fact, you will get the square root because this is the square of the amplitude. Now the issue is, I mentioned that in a real experiment we actually know the pressure, but we don't know the admittance here. So is there a way we can get this A, B and phi 1 minus phi 2 from measurements? So that is the next question. So phi 1 minus phi 2, phase is always one with reference to another, so it is not necessary to get phi 1 and phi 2 independently, but it is enough to find phi 1 minus phi 2. So the simplest way is we can see when this expression is a maxima and when this expression is a minima. When would this be a maximum? What is the maximum value of this expression? And what is the minimum value of the expression? A minus b whole square. So so we can say A plus B equal to P hat max and A minus B equal to P hat min, which should give A equal to P hat amplitude max plus P hat amplitude min over 2, B equal to P hat max So now we have determined A and B. Now we are left to determining phi 1 minus phi 2. How would you determine phi 1 minus phi 2, which is a simple way to determine? Can we think about it? The best way to look for is to find if we can locate the minima, let us say standing wave minima. So then what will be the value of this term at a minimum? This term should be -1 at a minima, +1 at a maxima. So when will this be -1? This is equal to pi, yeah. So you can say at a minimum cos of 2kx plus phi2 minus phi1 equal to pi, or 2kx min plus phi2 minus phi1 equal to cos pi. Now you could use the maximum also, but in general in a wave it is much easier to determine a minimum than a maximum, because if you look at the structure of a wave, at the maxima the value stays flat for quite some time. So we would have difficulty in determining which is the precise x location, whereas you can pinpoint this minima quite easily. And also if you look at the phase at the minima, the phase changes dramatically. So that is the reason why we go for determining the minimum value and using that to determine the phase phi2 minus phi1 rather than using a maximum. So in summary, at a minima the standing wave distribution is quite sharp, at maxima it is not quite sharp, therefore we choose the minima. Oh, I just plotted standing wave distribution. So this is a minima, I can surely pinpoint it because I mean it is from the pattern, but whereas the flat portion is, I mean it is not that hard to, I mean it is quite hard to pinpoint where exactly is the maxima, because for example you can imagine traversing a microphone, if the values do not change you do not know whether it is here or there, because over a big region the changes would be of the order of the uncertainty in the measurement. That is from practical considerations. In principle you can use the maximum also.
Having all these equations, we assume that p hat is at least twice differentiable with respect to x.
Yeah. So you are saying this is not differentiable. This is not. This is amplitude. So this is the amplitude. So we are taking a square root. That's why it's of this form. So if you look at the square, there is no problem. Okay. I mean this is a continuous function. It can be differentiated more than twice. And so this is the classical impedance tube technique, where so whatever I just mentioned is the known as the classical So there are two variants to this technique. One would be called 2 microphone technique, and another one is called multi microphone technique, or alternately can be called modified impedance tube technique. I personally think, well, I am not assuming anything. If you get the other way,
So then for A is P max minus P min by 2,
yeah,
and B is P max plus P min by 2, we also have the same solution.
yeah, so it will switch.
So we have two solutions.
Yeah, I mean, but that's okay, as long as you pick one, you are fine. What you call A, you will end up calling B.
We associate A with A power I kx and B with minus kx.
Yeah,
So we basically have two amplitudes for the plus kx term and minus kx term.
You are saying
Because-
that if A can be, if I take the minus sign here.
Sir, there sir, P min square is A minus B whole square.
Yeah.
It can be, P min can be B minus A
Yeah.
instead of A minus B.
Yeah.
In that case, B will be P max plus P min by 2, and A will be P max minus P min by 2.
Yeah.
So that would mean the amplitude of the e power I kx term will be lesser, and amplitude of e power minus I kx will be higher. And Phi1 and Phi2 are they don't really depend on the choice of A and B.
Yeah. Right. Yeah.
So
One
we-
second. Let me just think about it. So I mean, from what you're saying, this A and B can reverse. Yeah, it can reverse, but I thought that still wouldn't.
But there's no x. Just maintain x in the problem.
They are associated with different kx terms. One is minus and one is plus.
Okay, let me think about it and get back to you. But you are saying that I assume that A is greater than B? No. Yeah, okay. Implicit in that is A is greater than B. So let me think about it. I don't have a clear answer. I think both are okay, but let me get back to you. Sorry about this. I don't.
Shouldn't it be like b greater than a? Because if you take the problem in its, if you take the problem, then there's power going this way, but I mean not more power.
More can come in that way also. I mean, if there is some flame sending in the power.
No, but I mean in this particular problem at least it will be that b is greater than.
B can be greater or less. So I think you will have to choose it such that depending on the way the power is going in or out.
In that case, you said the final objective is to know if the system grows or decays.
Yeah, so let me get back to you. I am at the moment being stumped on this one. I'll give the answer tomorrow. At the moment, friends, working. Okay, sorry about this. So we'll get back to this sign thing tomorrow. At the moment, I'm not recalling the answer. So we can have, suppose we are unable to traverse or something in experiment. That's possible. If somebody gives you an engine and you cannot put your microphone inside and traverse, and you are not allowed to drill 20 holes, then one possibility is to keep the microphone at 2 specific locations, and then you have to know x the locations. You are a fixed x, and then you have to make the pressure measurements, both the amplitude and phase at each of the locations, and then we can also determine the pressure and velocity fields. That would be one thing. I would not go into it, but you can read up on this. Another one is what is called multi-microphone technique. So you can see that if you make many measurements, you can actually do a curve fit, like a least square fit for A, B, and Phi1 minus Phi2. So from that, you can actually get a better estimate of A, B, and Phi1 minus Phi2, but that would mean that you have to make many measurements rather than just rely on a measurement at a maximum and a measurement at a minimum. So that would be called multi-microphone technique, or the modified impedance tube technique. I think the multi-microphone technique sounds as a better name, but both essentially both the terms are used in the literature and they mean the same thing. Now we wish to recover some of the classical results from this problem. So let us look at the case of open end and closed end and see if we can recover these results. So So, I will for convenience denote this phi1 minus phi2 as phi, and then we can rewrite this as a squared into 1 plus b over a squared plus 2b over a cos 2 kx minus phi. So, if you think of a wave a e power I kx going this way, and if you can think of another wave b e power minus I kx, we can actually think of a reflection coefficient r, which is b over a. Let us for convenience we say that this is at x equal to 0, that is where we are determining the impedance or the admittance. This can be written as so this would be a squared into 1 plus now. So, now I have rewritten the expression for the standing wave in terms of a reflection coefficient. So, that is another way of writing the admittance or the impedance in terms of saying that I send in a e power I kx, b e power minus I kx comes out, and let us put our coordinate system such that this termination is at x equal to 0, and then a reflection coefficient can be defined as this complex number b divided by the complex number a. So, this is the equivalent definition of defining admittance. So, if you say a equal to b, then r equal to 1, that would mean r equal to 1 and phi equal to 0. So, this would be p squared equal to a squared into 1 plus 1 plus 2 cos 2 kx. This would be a squared into 1 plus this can be recast as so what is this termination actually? We worked out this problem earlier. When is reflection coefficient equal to 1, and when do you get this kind of pressure distribution? Closed in, yeah, rigid termination. So, this would be for a equal to b and r equal to 1 is for a so what we have this is like a general result, this distribution which we get, and we are able to derive this previous expression that we got for the simple standing wave with one end closed and one end open, which is 2a cos kx from that. Okay. So, now we can look at what happens when the reflection coefficient is minus 1. So this minus 180 degree, that 180 can be removed and you can put a minus sign here and then we can multiply. So this is 4 a square. So you will get so this is the other classical result which we had for reflection at a open end. This is what happens when B is 0? It's a progressive wave. So you don't have this wave pattern, standing wave pattern, but it will just be constant amplitude. So it's a traveling wave, okay, when B equals 0. Or traveling wave. No reflection. So we actually have the pressure distribution. Now what we need is to determine the acoustic velocity, and then once you have an expression for acoustic velocity, we can determine the acoustic velocity at your x equal to 0, and then the admittance is just acoustic velocity amplitude divided by complex amplitude divided by the acoustic pressure amplitude, both are complex amplitude. So how do you determine acoustic velocity? Rajesh, how do you determine acoustic velocity? This is the fatal mistake we all make. In fact, I must warn you that acoustic pressure divided by rho c will be the amplitude only if it is a right running wave. If it is a left running wave, what will be the velocity? And we have both left and right running waves. So you have to take the amplitude of the right running wave divided by rho c minus amplitude of the left running wave and divide by rho c. So in general, pressure divided by rho c is not a solution, because pressure is of the form F plus G and velocity is of the form F minus G over rho c. So you take your F plus G and divide by rho c, that is not equal to acoustic velocity. Is that clear? So let me just restate this. Acoustic pressure is of the form F of x minus Ct plus G of x plus Ct, and acoustic velocity is of the form 1 over rho bar c F of x minus Ct minus G of x plus Ct. So in general, u prime is not equal to p prime over rho c only for a right running wave, u prime equal to p prime over rho c, and for a left running wave, u prime equal to minus p prime over rho c, because this is because a wave which is going to the right, if you think of a compression wave going to the right, the gas will move to the right, the same compression wave of the same amplitude. If it is going to the left, gas will move to the left. So that is why velocity has a direction associated with it, that is why the sign changes, whereas pressure is just it does not have any direction. Is that clear? Yeah, if you have to take both together, how do you do it? That was my original question. Yeah, but we do not know B and A yet. So that's the thing. Yeah. So in general, how do you get? So we can use the what equation? Linearized momentum equation, absolutely. So the linearized momentum equation, if given pressure you can determine velocity from the linearized momentum equation. I think we should write in big letters. So in the harmonic domain you have u hat equal to minus 1 over I omega rho bar dou p hat by dou x, and again it is quite important to remember whether you are using e power I omega t or e power minus I omega t, both are completely okay, but we have to use one from start to end, because if you use e power minus I omega t you would not have, your sign here would be different, your wave equation and Helmholtz equation would be same, but the sign would be different, but in the end the answer would still be the same, because when you in the end take the real part you will get the same expression, but you have to keep track of what you are using and use it consistently throughout your exercise. So we know that p hat was a e power I k x plus b e power minus I k x. So u hat equal to minus 1 over I omega rho bar into dou p by dou x, that would be a e power I k x, I take I k out. If I differentiate e power I k x I get I k, if I differentiate e power minus I k x I get minus I k. So once we have A and B and phi, that means we essentially have capital A and capital B, so you can actually get the velocity and then you just have to divide this velocity by the pressure and you will get the admittance, right? Is that clear? So just to go back to remind you of the definition, admittance y was defined as u hat over p hat at whichever surface you want, and here it is x equal to 0. I have chosen my coordinate system that way, and I also have the non-dimensional admittance script y or capital Y as y divided by 1 over rho c or rho c times y. So this would be equal to, I think I missed a sign, yeah, I should have a minus here, yeah, thank you. So we know A, capital A, we know B, capital B. So therefore we know the value of y anywhere. So we can know at x equal to 0 also. So that is basically the crux of the matter. Once you have that small a and small b, we have actually solved the problem. So if you look at y at x equal to 0, this will be minus, if I divide by a, I will get 1 minus b over a divided by 1 plus b over a, which is equal to minus 1 minus r divided by 1 plus r, which is same as minus 1 minus so we can do some algebra and separate it into real and imaginary parts. I will just write down the final expression. We can check it at home. Y real equal to minus 1 plus r squared divided by oh this is capital actually, sorry, so I should, thank you. So I want to give you a homework, please do it. Did show that the phase, so if theta of x equal to tan inverse a sin kx minus b sin kx minus phi divided by a cos kx plus b cos kx minus phi, which is same as tan inverse sin kx minus r so derive this expression for phase and then show that find the limits when you have a left running wave and a right running wave. So please do this at home and we can look at the results next tomorrow. Thank you.